So in this section we're going to have a look at the hydrolysis of peptides. Now this should be relatively easy because we've done this in polymers earlier on in the course. So hydrolysis is the breaking of bonds using water, and we had acid hydrolysis using 6 mole per decimetre cubed hydrochloric acid, and our conditions were going to be that we're going to reflux it for a fairly long time. Okay, so when we're doing hydrolysis, what we need to think about is that we are going to break that peptide bond. So remember that this is a peptide because of this peptide bond. So we're going to break that peptide bond, and we're going to break it using water. So the first thought process that we would have is, let's break it using water. So we're just going to copy out the 2 parts. So that's the first part that I just broke that bond. I'm just going to go over here and copy the second part. So I've just broken it up into 2 parts. We've got 2 amino acid residues here. And I'm going to break it using water. So I'm going to put that water, remember that water is H2O. I'm going to break it using water, and I've broken that peptide bond and I've put that water back in. But I must stop and take a minute and check whether those products can exist under these conditions. So look back at the conditions, and the conditions, 6 molar HCl. And what would acid do to an amino acid? Okay, so these are amino acids. Amino acids contain amines. So what I'm going to do is I'm just going to move these protons around a bit, these hydrogens around a bit. Because amino acids are amines, the lone pair on the nitrogen can accept a proton to become an ammonium salt. And we've got the counter ion from the hydrochloric acid. So just be careful, check everything. Is there any group present that reacts with acid in this case? So that would mean if there were amine groups in the R chain, the side chain, we would need to adjust those as well. Acid hydrolysis. Alkaline hydrolysis, how would that be different? So again, we're going to use moderately concentrated, maybe not quite 6 molar, but moderately concentrated sodium hydroxide. So there's going to be some water present because it's not the solid. And we're going to reflux it again for a long time to get this to break. Your body is amazing. The enzymes, the proteins in your body can break down this without having to reflux it in really concentrated things for a long period of time. Every time you eat, you don't need to set up a reflux condenser in your stomach. So we're going to break our peptide bond. We're going to copy out our 2 residues. So remember that we had a hydrogen, it's a bit high up that. We had a nitrogen with 2 hydrogens on the left, and a C with a H, and a CH3, and then a C with a double bond O. So at the moment I'm just copying where I've broken it. Okay, so I've copied it out. I'm going to put the water back because that's what hydrolysis is. And then I'm going to consider the effect of my conditions on my products. Now remember that that is a base, sodium hydroxide, so it's going to react with any acids. And we've got acids, so I'm going to lose the proton. I'll just have to tidy that up because it's a bit tight in space. So I'm going to lose that proton because it's going to donate it to my sodium hydroxide, and then the sodium ion will float around. And then I'm going to lose the proton from this side to make the salt, and my sodium ion will float around. So watch out that the conditions will affect the products that you get. So the structure of the products depends on the pH at which you hydrolyse it. pause the video and have a go at this question. So the first question asks us how many amino acids are present. So what I've done is I've drawn a red line through every peptide bond. So there's actually a peptide bond at the end here where it joins to the amino acid that's not shown, and between the C double bond O and the N, the C double bond O and the N, the C double bond O and the N, and so on all the way down. So we've got 1, 2, 3, 4, 5 amino acids. So I've circled around some of the peptide bonds. I've actually named the amino acids on my diagram as well. So I've got aspartic acid, then alanine, then cysteine, then alanine, and then phenylalanine. You can use your data sheet to name those. You'll find the names on the data sheet. Now it wants us to give the structure of the right-hand amino acid, so the phenylalanine, but when we have hydrolyzed it under acid hydrolysis. So the first thing I'm going to do is draw out that little section, that residue that is phenylalanine, and then we're going to see what it would look like in acid conditions. So there we go. I drew the phenylalanine residue part in black. That was just copying from above. The blue is where I've put the products of the hydrolysis back, the water, to create the bonds. And then the green is the effect of it being in acid conditions. So I have another go on the left-hand side one, so that's the aspartic acid in alkaline conditions. So we would have put the water back on both ends, and then in the alkaline conditions, we don't know what the counterion is, so we don't know whether it's sodium or potassium. The protons from the acidic groups, but watch out, notice that there are 2 Cu groups in this, and so both of them will be deprotonated. Okay, so that's our little section on hydrolysis.